All right, class, welcome to this module, the motion of ions. So we're going to look at how ions move in solution. So this, we'll look at introduction, the drift speed, we'll find out what drift speed is, we'll explain the drift speed, look at mobility and conductivity, and we'll conclude. There are so many questions that need to be answered for us to be able to interpret conductivity measurements. Now, for example, why do ions move at different rates? That's a very big question. Two, why do we have different molar conductivities? And why do the molar conductivities of strong electrolyte decrease with square root of concentration? Remember, these are the things we have seen. And these are questions coming up. So we need to have solutions to these questions. To have solutions to the above observation, we shall rely on the fact that the greater the mobility of an ion in solution, the greater the contribution to conductivity. You see, when I was saying if you're moving against air current, the greater the mobility, the greater your movement, will be the greater the contribution of that person to whatever you want to do at that point in time. So look at the drift speed. Now if we consider two electrodes, the distance is L and the potential difference is V, and they are in, experiencing, the ions are experiencing uniform electric field. The electric field E will be equal to the voltage divided by the distance. And in such a field, if the charge is ZE, it experiences a force of ZE multiplied by a capital E, which is same as ZE V over L. From here, E is V over L, so you substitute for E here. As the force acts on the cation and anion, this is a force that acts on the cation and ion that makes the negative, that makes the cation to move towards the negative, that is the positive ions to move towards the negative electrode, and then the negative ions, that's the anions, to move the positive electrode. Remember we said, charge species will move to opposite electrodes. Also, the ion experiences a frictional force. There will be a frictional force as you're moving. Because in solution, it looks like something is driving it back. That's the frictional force. And when we talk about frictional force, then we'll bring in Stokes' law. This is frictional force from Stokes' law, where A is the radius and then the viscosity. So if we equate that, we have the force of that frictional force will be equal to Fs. Therefore, which means when this ion is balanced, we have that force will be equal to the frictional force. And when that happens, the speed of this ion will be equal to Z small e multiplied by capital E over F. And at this point, we said that the ion has reached a terminal speed, which we call the drift speed of the ions. So this equation 4.5 gives us a value of the drift speed, having considered the Stokes' law, having considered the force on the ion on application of electric field. So this gives us the drift speed. We're also going to see where this drift speed is in relation to mobility. And when we talk about this drift speed, it's just like when somebody is floating, maybe something like one who is in a lift. At some point you feel this weightlessness and it looks like the person is drifting. The force forward and the force backward equals each other. Fine, we want to do a little explanation of this drift speed. Now from experiment, it is confirmed that conductivity decreases with increased solvent viscosity. What is solvent viscosity? Thickness of a solvent. So when that solvent is thicker, I don't know how many of us remember the experiment we do in secondary school for Stokes' law. You bring different, solvents, kerosene, engine oil, crude oil, and so on, with different viscosities. we'll now take a bearing, a small bearing, measure use vernier caliper and measure the area of that bearing so that, the diameter of that bearing, so we'll be able to calculate the area. Now we'll use it to drop in those different liquids and use our stop clock or stopwatch to find out the time it takes for that little bearing to fall from the beginning of that big cylinder to the bottom. So if the viscosity increases, then it means that movement will decrease. That's what we mean by conductivity will decrease with increase in solvent viscosity. This is of course expected since the drill speed governs the rate at which charge is transported. Now, but what we look at these in terms of small ions and bulky ions, and then you need to go back to your periodic table. We know that there are periodic properties, variation of properties, across the period and down the group. So what we're trying to say here is that small ions with very large field will now attract water molecules, because the A in Stokes' law is what we call hydrodynamic radius. It's not just the ionic radii or ionic radius of any particular ion, but it measures also the ionic radius of all the species, that is the water molecules attracted by it. So the stronger the force that's the charge on the ion, the more water molecules it will attract. So the hydrodynamic radius increases, which affects its conductivity. The same thing follows. It then follows that small ions will generate higher electric field, exactly what I said before, and hence carry more water molecules around it. Thus, the hydrodynamic radius is defined as effective radius in solution, which takes into account all water molecules in its hydration sphere. So small molecules will attract more water molecules, and in fact now have higher hydrodynamic radius, which affects its mobility and conductivity. This means that an ion of small ionic radius may have a large hydrodynamic radius because it drags many solvent molecules. In fact, in a higher level, we'll start talking about not only this mobility, but we'll also start talking about electrophoretic effects and so on. Mobility and conductivity. Now we're trying to look at the mobility. How is it related to conductivity? So we did an analogy here. When we consider the solution of strong electrolyte and molar concentration C, the ions will be Z plus E or Z minus E. And of course the concentration will be Vc, where V can be V plus or V minus depending on the ion, and the number density will now be this Vc multiply the Avogadro's number. Therefore the drill speed will now be for cation or anion. So we'll have S plus and S minus. Now the number of ions that pass through an imaginary window, we're not talking about flux, through an imaginary window at interval delta t, which is the time, will be equal to S dt. Therefore, we now have this as equal to the number in that volume. So this gives us the number of ions in this volume will now be equal to this. Remember, we just got this from here, and then we got this from the number density of the ions. So when we talk about the flux, is given by this. If we now cancel out like terms here, we'll have SVC and A. Now, but when we talk about flux of charge, we'll bring in ZE, which comes in here. Z is introduced here, and E is also introduced here. But then, Avogadro number, 1 Faraday, is equal to charge multiplied by Avogadro number. And of course, S is equal to UE. So if we substitute, this equation becomes equation 4.9. And the current I flowing through the window is equal to the flux times the area. And that gives us this. And of course, E is equal to V over L. We also obtain this. So here, we just played around with this flux in terms of flux of charge, in terms of flux of current, and of course in terms of electric field, and we'll get all these equations. And also we forge ahead for Ohm's law. From Ohm's law, current is equal to V over R. And if we combine there, we'll get this by also remembering our specific conductivity. And of course, we arrive at this if Vc is the concentration. Therefore, we can separate this into the positive and the negative ions. And this gives us this very important equation for symmetrical, that is 1:1 electrolyte, as the limiting molar conductivity is equal to this, given by equation 4.16. So thank you very much. We looked at drift speed, explained drift speed, and looked at mobility and conductivity. See you in the next class. Thank you.